Right, so twice continuing the previous videos, we talk about the Instanton and Sphaleron. In the previous video, we talk about the topological solution. So there's some spontaneous metric breaking as SB from the symmetry G to the G of the H. To the H is the remain symmetry, and the G of the H is the correspond to the generalized vacuum. And we can assign the partial infinities like as L for the n-dimensional and minus one dimensional space-time. We can assign the such as partial infinities to those degenerate vacuum sites, and we can classify the its solutions topologically, physical topological solution. And we discussed the kink vertex on the first and instanton. And so we focus on instanton and the spirals, especially spirals unstable solutions. So the instances that comes from the 3 plus 1 dimensions in the Young Mist theory. There is a weak rotation with the imaginary sign. So in the original Minkowski space-time, the solution is given by the tunneling with the such a potential. But after the weak rotation of the imaginary time, it becomes a Euclidean space-time, and the potentials are swaps because of imaginary time. So the particles behaves like the propagations over the potentials. The Yang-Mills auction is given by such a form. One of those two disks with couplings and the twice of the Beer-Strongs. And to get the finite taxon solutions, the Beer-Strongs at the spatial infinity should be zeros, namely. And because the Beer-Strongs defines as the commutative relations of the covariant derivatives around the vector field A mu, so A mu should be also the zeros at the boundary or infinities. There's also a Yang-Mills case transformations review. So the spin-off is the transforms with the transformation matrix U with the generalized tau and the parameter setup. And with the covariant derivative, this is transforms case in covariant. So the psi bar d mu psi becomes a case invariant quantity. And the non-abelian case boson transforms like that. Its addition is a non-abelian term. And at the axis infinity, with the specific pure cases, it transforms like such widgets. Similar to this previous videos, there is a set of infinities that is caused by the three-dimensional space. Yeah. And the original symmetry is given by the SAT case group, and this is isomorphic to the S3. And such gauge groups are spontaneous symmetry vacuums to the just singular groups with just identity. So the degenerate vacuums or zeros are given by the SATs of the ones as a quotient group. So if we think about the third order homotopy groups of the S3, so this S3 is a degenerate vacuum, and the pi 3 is the correspond to the three-dimensional space as a set of the spatial infinity. Then the homotopy groups is the jet as a winding number. This is the proof why the SAT is isomorphic to the S3. This is a 2x2 matrix with complex numbers and the determinant should be the 1. So that this gives the condition for the three-dimensional spinors which lives in the 4 dimensions. So by this box, the third homotopy groups of the S3 is equal to the integral stat jet. So it corresponds to the winding number Q, which can be obtained by the this right-hand side, twice of the ab minus and the dual tensors ab min theta. So this gives the winding number. So it can be interpreted like that. So in the Euclidean space, there's a boundary that is described by such a sphere S3. So No, this is the Minkowski. And this is Euclidean. So this is a Minkowski and this is Euclidean. And in the Minkowski space-time at the boundary, the base strength immunity and the gauge bosons shift the zeros at the pure gauges. But in the Euclidean space, this is after the Wigler torsion, so the time becomes imaginary time. But there is a boundary, and the gauge boson solutions are propagates from the here to there. So propagation of Euclideans against the same turnaround in the Minkowski space-time. There are some several boxes in the Instanton solutions. Also, there are different vacuum, and this can be described by the assigning the vacuums like n and n plus mu. Instanton solutions are correspond to the tunneling as a vacuum-to-vacuum transition solutions. And there's a set of vacuums as a superposition through generalities through vacuums, and there is actually two vacuums. And such a winding numbers are related with anomalies coming from the triangle diagrams in the quantum field theory. So because of such a triangle diagram, it gives anomalous word identity, which is the conservation through current is broken. So left-hand side is a continuity equation, but the right-hand side non-zeros by this non-zeros winding number. So if we integrate this current to obtain the difference of the charges at the time infinities to the past infinity, so difference of the winding numbers changes along the time. So this is a summary for the topological solid term. I already started it when I start this video. So there's a partial homogeneity at infinity as n. And there's a horizontal vacuum which is described as G over the H's. When the symmetries are broken from the G to the H's. And to have the finite analysis solutions, the special infinity should be the map to the observed vacuum, and they can be classified topologically. And the solid term means that the solutions are given by the dispersion loss. So it's the Clocks locally as specific pointed. So the topological classifications are given by the anti-homotopy groups of the G of the H's. For example, in the one dimensions, the special infinity given by the S-G, and the pi G's, and the symmetries are broken from the G2 to the 1. So the pi G's of the G2 symmetries are just given by the G2. This is a king. And the two dimensions with special infinities with S1. So pi 1 sort of the U1, it gives a vertex with the winding number. And the three dimensional pi 2 sort of the SO3 to the U1 symmetry breaking, it gives also the winding numbers, which describes the number solutions. And the 3 plus 1 dimensions, CT Yang-Mills gauge series are broken, and this gives the intersection winding numbers, and this is the Instanton solutions. And such a winding numbers can be described by the anomalous like this. And if we integrate through over the current to obtain the difference of the charge, and this is called the Chern-Simons number, which is also can be denoted by the MCS. So this is a discussion of an Instanton, and also now I want to talk about the Instanton light. The transition light is given by the exponentials of the -2 times the Euclidean actions. This can be proven by the such as stuff. First of all, the difference of the various strengths at minus and the dual, and the scale sort of stars always has becomes a positive semi-definitions. And if we expanded this, then they gives the two Euclidean action term, and the up theta, which is cross term, gives a Chern-Simons number. So by using this inequality, the Euclidean action is larger than the Chern-Simons numbers with additional factors. And if we keep the Chern-Simons numbers as a 1 as a minimum number, and such a transition light has upper bound, which is given by the gauge coupling. And if we insert the gauge coupling in here, then Instanton light is almost 100 minus 170 is too small. And this is the zero temperature region. So Instanton is how to be occurs, and actually such Instanton the light is with the barrier number violations, because there's such a winding number of Chern-Simons numbers across form to the some some of the charges with the global symmetry, like U1B symmetry, baryon symmetry. So we want to make the enhance such like one possible approach is Polaron. Polaron is also the sum of the specific solution of the Yang-Mills theory, but there's a one negative is eigenvalue. So there's a certain point in the some specific directions that in that direction the solution becomes unstable. Since the Polaron solution is static and the finite energy. So there are some descriptions through the certain point here. So acetus Polarons are also described by the Yang-Mills actions. Some is again by the similar form. And at the zero sort of potentials, the zero sort of potential and the spatial infinity is assigned to the zero sort of potential. So we can assign the solutions for the acetate Higgs and the Gaze field as a spiral solution. So this is some descriptions of the spiral solution. In the Chern-Simons number instructions, there's a negative eigenvalue. So we can assign the y number nu equal to the 1/2 as a fraction of such Chern-Simons numbers. It becomes spiral. And because there are a potential barrier here, that there's a spiral energy, which is the lattice with the finite temperatures regions. So spiralons are like this following. So there's axial current for the baryon number. And there's the anomalies for the baryon numbers and Lofton number is given by the such a form. W minus and W minus theta your tensor. So there's a continuous equation. So baryon numbers and Lofton numbers are lattice for each, but the P minus S numbers are constant. And if we integrate over the space-time, then we can assign the difference of the Chern-Simons numbers, and this becomes an integer. So t becomes an integer, there's a just case, which is just again by the fractionless numbers coupling. But so the space function has proportional to 1 over the z. And the energy is given by the W minus and W theta. So the energy is proportional to the 1 over the z scale. So the Polaron's energy is proportional to the 1 over the z scale. So that's energy values of the potential. And by using the dimensional analysis, there's the way without some of the mass parameters, which comes from the W gauge also in the Yang-Mills theory. And in the exact solution, there is additional order of the 1 factors as corrections, and the Polaron energy is almost 8 to the 14 TeV. So by using this Polaron's energy, we can calculate the Polaron light with the finite temperatures. So instantaneous just tunneling solutions from the one vacuum to the other vacuums in the such potential. The Polaron is unstable solutions of the potential area. So Polaron light is proportional to the such expansion minus energy of Polaron over the T as opposed to Bactis. So that this Polaron light is actually the light for the volume. So that is proportional to the addition of Bactis with the constant factor C and the temperature dependence T to the 4 power. Such formulas are only holds for the low temperatures. So when the temperature is smaller than the Polaron energy. But in the high temperatures, the temperature other than the Polaron energy is the EPFs like such a form. So by using this box, the Spiralons, we can obtain the Spiralons temperatures in the early universe. The spiral light should be the ladder and have light, which is given by the C-squared related to the Planck's mass. So that we can separate this in the case, but in the high temperature, we should use such alpha service to the 5 powers T formula, and this gives the upper bound of the Spiralons. Upper bounds of the Spiralons occurs in the universe, and the second case in the low temperature inequality gives the low bounds. So Spiralons occurs at the temperature 12 GeV in the universe, and the Spiralons decouples at the 100 GeV, so which is the order of the electron symmetry making. So this is a very important in the baryogenesis and optogenesis, because Spiralons as the concept of B minus L, so it can transit from the lepton symmetry to the baryon symmetry. So optogenesis can provide the baryon symmetry through the universe. Lastly, I want to focus on the Spiralon factors, how there is a relation between the lepton and the baryon number. For the particle i's, there's a chemical potentials. And the chemical potentials can come from the hypercharge contributions from the U and Y. symmetry and the B minus L charge contribution, which is the U1 B minus R global symmetry. For example, if the R is the neutrinos, then we can calculate from the B minus symmetry some hypercharge. For example, Higgs, there's no B minus charge. And in the previous videos, we discussed the number densities of the universe. For the barometers, the number density, especially the difference between the particle and antiparticle symmetries, are given by the chemical potentials. The barometer case, and for the boson case is just given like that. With also the symmetries are related through the chemical potentials for the boson case. So particles and antiparticle symmetries can be expressed in terms of the chemical potential that's the point. But there are several particles like the lepton, quarks, and the Higgs. So the last denotes the new apps, the number of the barometer generations in the standard model is 3, and the new apps, the number of the Higgs double laws in the standard model is the 1. So the first ones correspond to the neutrinos and the lepton. The symmetries between the particles and antiparticles number density, which is related to the chemical potentials. So we already calculate the chemical potentials in the first step. And for the right hand is lepton, and left hand is quark, right hand is up quark, right hand is down quark, and the Higgs. So by using those numbers, particle and particle symmetry in terms of the chemical potentials, we can calculate the going on. And in the universe is electric neutral, and such electrical charges is related to the hypercharge. So U1 EM is related to U1 hypercharge. So the summations of the hypercharge times of the number of symmetry should be the 0. By using this fact, we can find the relation between the chemical potentials from the B minus charges and the chemical potential from the hypercharge. So we can remove the mu, which is chemical potentials contribution from the B minus charges. So by this fact, we can calculate again that these formulas number of symmetry particles and antiparticles, the symmetries for each particle in terms of also only the mu y. We can remove all the mu. So now all the ingredients are ready. So this is a baryon number, which is given by the Kirk, and antiquark symmetry with one of the third factor. So it can be written in terms of the number of the barometer generalized and the number of the Higgs stabilizer and the chemical potentials concentration for the hypercharge. And similarly, the leptons comes from the neutrinos and other lepton. So B minus L also can be calculated. And by calculating the relationship between the baryon numbers and the B minus L, we can now define the parallel vectors in terms of the new app and the new S. So this is the parallel vectors. And if we insert the new app equal to the 3 and the new S equal to the 1, that is the parallel vectors, 28 over the 79. So today we discussed the Instanton solutions as one solutions as of the Yang-Mills theories, and it gives the Chern-Simons numbers from the anomalies and the winding numbers, which comes from the topological classifications. And in the next, we discussed the Sphaleron as unstable solution of the Yang-Mills octagon, and they should requires the some finite temperatures corrections for the Sphaleron light, and we can find the Sphaleron intervals in the early universe. And finally, we calculate the Sphaleron vectors by using the chemical potentials and the number density for the particle and antiparticle symmetry.